But then there's this story that you will hear that Einstein couldn't quite cope with quantum mechanics, right?
The realm of physics has been profoundly influenced by the monumental contributions of Albert Einstein. His groundbreaking theory of relativity transformed how we perceive space, time, and gravity, equipping us with the framework needed to explore the universe. For more than a century, his work has been a pillar of contemporary science. However, the rapid development of quantum computing is now shaking the very bedrock of physics, challenging even some of Einstein's most foundational theories. It's not merely that quantum computers outpace traditional ones. They function according to principles so unconventional and paradoxical that they compel scientists to rethink our fundamental understanding of the universe. These advancements carry consequences that are truly revolutionary. Let's start by examining quantum computers themselves and understanding why they are so radically different from the classical machines we've relied on for decades. Conventional computers handle information using bits, which can either be 0 or 1. This binary system is the core of everything from mobile phones to supercomputers. In contrast, quantum computers rely on quantum bits or qubits. Unlike bits, a qubit isn't limited to just 0 or 1. Due to the principle of superposition, a qubit can exist in multiple states at once. Picture flipping a coin. Instead of landing on heads or tails, it could land on both simultaneously. This unique feature allows quantum computers to process vast quantities of data in parallel, solving problems that would take classical computers millennia to finish. But that's not all. Another remarkable characteristic of quantum computing is entanglement. When qubits become entangled, the state of one qubit is immediately connected to the state of another, regardless of the distance between them. Alter one, and the other changes simultaneously. It's as if by magic. This strange phenomenon baffled Einstein, who famously described it as spooky action at a distance. He struggled to accept that the universe could operate in such a way. Einstein's worldview was grounded in an orderly, deterministic universe. He once claimed, God does not play dice with the universe. However, quantum mechanics suggests that the universe is governed by probabilities, not certainties. At the quantum level, events do not unfold according to a rigid blueprint. They are driven by probabilities. This inherent randomness contradicts Einstein's perception of a fully predictable reality. For decades, these strange quantum principles existed mainly in the realm of theory, debated in academic settings with minimal practical use. But this has now changed. With the rise of quantum computing, we are starting to apply the peculiar rules of quantum mechanics to real-world problems. These developments are challenging some of the most fundamental assumptions of physics. A major breakthrough comes from quantum computers' ability to simulate quantum systems. Classical computers struggle to model complex quantum interactions because the calculations become increasingly difficult as the system grows. Quantum computers excel in this area, simulating quantum systems with remarkable precision. This capability enables scientists to test hypotheses and conduct experiments that were previously out of reach. Now, here's where it gets even more intriguing. In 2023, researchers used quantum computers to simulate certain quantum phenomena that defied Einstein's equations of relativity. These simulations uncovered inconsistencies in how quantum particles interact with space-time at the smallest scales. While Einstein's theory of relativity is highly effective in describing large-scale systems like planets, stars, and galaxies, it falters when applied to the quantum scale. At this level, space and time, which Einstein portrayed as smooth and continuous, appear fragmented and discrete. Quantum computers have provided the first direct evidence that space-time may not be the seamless continuum Einstein envisioned. Instead, it may resemble a pixelated structure akin to the resolution of a digital image. Although this idea isn't entirely novel, concepts like quantized spacetime have been explored in theories such as loop quantum gravity. Until now, there has been no way to experimentally test these notions. Quantum computers are now enabling these tests, potentially revolutionizing our comprehension of the fabric of the universe. Another area where quantum computing challenges Einstein's legacy is causality. In classical physics, cause and effect follow a clear and predictable sequence. One event leads to the next in a linear fashion. However, quantum mechanics introduces a concept known as indefinite causal order, where the sequence of events is unclear. Imagine two events, A and B. In the classical world, A happens first, followed by B. But in the quantum world, A and B could exist in a superposition where neither clearly occurs before the other. This challenges our classical understanding of time and causality, central components of Einstein's theories. The consequences of this are profound. If causality can be indefinite, it raises questions about the very nature of time. Is time a fundamental aspect of reality? Or is it an emergent phenomenon, a result of deeper quantum processes? These are questions that quantum computers are helping us explore, and the answers may fundamentally change how we view existence. Perhaps the most startling revelation lies in the potential link between quantum computing and consciousness. Quantum mechanics has long been tied to the mysteries of the mind, ranging from the observer effect to the role of consciousness in collapsing quantum wave functions. Some researchers are now using quantum computers to investigate these connections, attempting to simulate the quantum processes that could underpin thought and perception. One hypothesis suggests that consciousness itself could be a quantum phenomenon, emerging from entangled networks of neurons in the brain. If this theory proves correct, it could revolutionize neuroscience and challenge our understanding of identity, free will, and existence. Beyond these intellectual revelations, quantum computing also raises a host of practical and ethical considerations. One major concern is that the immense power of quantum computers could render current encryption methods obsolete. Modern cybersecurity depends on the difficulty of factoring large numbers, a task that classical computers would take millions of years to complete. Quantum computers, on the other hand, could solve these problems in mere seconds, potentially exposing sensitive data and sparking a cybersecurity crisis. On the positive side, quantum computers also offer solutions to this dilemma. Quantum encryption methods, such as quantum key distribution, are virtually unbreakable. These systems leverage the principles of quantum mechanics to ensure that any attempt to intercept or alter data is immediately detectable. Another significant concern is how quantum computing will affect the global balance of power. Countries and corporations are racing to develop quantum technologies, aware that control over these innovations will confer a massive strategic advantage. This new quantum arms race could reshape geopolitics in the 21st century, much as the space race did in the previous century. As we stand at the precipice of this quantum revolution, it is clear that its implications extend well beyond science and technology. Quantum computing is forcing us to confront deep philosophical questions about the nature of reality, the limits of human knowledge, and our place in the cosmos. Einstein's contributions to physics will always be monumental, and his theories remain invaluable for understanding the macroscopic world. However, quantum computing is revealing that his vision of the universe was incomplete. The quantum realm is much stranger and more intricate than Einstein could have imagined, and we're just beginning to scratch the surface. This isn't just about proving Einstein wrong. It's about building on his legacy to uncover deeper truths about the cosmos. As quantum computers advance, they will continue to challenge our assumptions and stretch the limits of what we thought possible. The real question isn't whether Einstein was wrong. It's how his ideas have paved the way for new frontiers to explore. The quantum revolution is here, and it's reshaping our understanding of physics, technology, and reality itself. Quantum computing is more than just a technological leap. It's a paradigm shift in how we perceive the universe. In this expanded discussion, we will explore the ongoing scientific breakthroughs within the quantum revolution, how they intersect with Einstein's foundational theories, and the ripple effects across various disciplines, including cosmology, biology, artificial intelligence and ethics. Quantum computing is bridging the classical and quantum worlds, and one of the most remarkable aspects of this technology is its ability to connect two seemingly contradictory views of reality: the deterministic world of classical physics and the probabilistic nature of quantum mechanics. Einstein's theories, particularly general relativity, are based on a deterministic framework. In this framework, space-time is a smooth, continuous fabric, and the movement of objects within it follows predictable rules of causality. On the other hand, quantum mechanics operates on entirely different principles. At the quantum level, particles act like waves, existing in multiple states simultaneously until they are observed. This duality and probabilistic nature make it difficult to reconcile quantum mechanics with the smooth, deterministic space-time that general relativity describes. Quantum computing offers a unique bridge between these two worlds by simulating quantum systems on an unprecedented scale. With the help of quantum computers, we are now able to explore the interface where classical and quantum physics meet. This is where some of the most groundbreaking discoveries are taking place. For example, quantum computers are being used to simulate black holes and other extreme environments where quantum mechanics and general relativity collide. Black holes, with their intense gravity, warp space-time to such an extent that Einstein's equations no longer hold true. By simulating these extreme conditions, quantum computers are helping us understand phenomena like Hawking radiation and the enigmatic information paradox. The information paradox, initially proposed by Stephen Hawking, arises from the conflict between quantum mechanics and general relativity. According to quantum theory, information should be preserved when matter falls into a black hole. However, Einstein's equations suggest that this information is lost forever. Quantum simulations are helping scientists unravel this paradox, bringing us closer to a unified theory of quantum gravity, something Einstein himself sought but never attained. At the heart of the quantum revolution lies the quest for quantum gravity, a theory that would reconcile general relativity with quantum mechanics. Quantum gravity aims to explain how gravity behaves at the quantum level, unifying our understanding of the very large and the very small. While Einstein's general relativity explains gravity as the curvature of space-time caused by massive objects, it doesn't apply at the quantum scale, where space-time becomes granular and probabilistic. Quantum gravity seeks to describe how these quantum fluctuations in space-time lead to the macroscopic gravitational effects we observe. Quantum computers are playing a vital role in this quest, simulating the quantum fluctuations of space-time and revealing patterns that were previously inaccessible. One particularly exciting development in this area is the holographic principle, a concept rooted in string theory. The holographic principle suggests that our three-dimensional universe is actually a projection of information encoded on a two-dimensional surface. Quantum computers are now being used to simulate holographic models of space-time, offering new insights into the very nature of reality. If space-time is indeed holographic, it would fundamentally alter our understanding of the universe. It would mean that the reality we experience is not the deepest layer of existence, but rather an emergent phenomenon like a cosmic illusion. Quantum entanglement, the spooky action at a distance that so disturbed Einstein, is emerging as a crucial element of the fabric of reality. Recent research suggests that entanglement is not just a quirky feature of quantum mechanics, but maybe a fundamental building block of the universe itself. Physicists are exploring the idea that space-time itself could emerge from a vast network of entangled particles. This concept, often referred to as quantum geometry, proposes that the structure of the universe at the smallest scales is determined by the entanglement relationships between particles. Quantum computers are uniquely suited to model these relationships, offering a new perspective on the origins of space and time. One groundbreaking experiment involved using entangled particles to create a quantum wormhole. Wormholes, shortcuts through space-time, have long been a staple of science fiction. But recent research suggests that entanglement could create structures resembling wormholes, connecting distant regions of spacetime. Quantum computers are being employed to simulate these wormhole-like structures, offering tantalizing clues about the interconnected nature of the universe. If entanglement is indeed the foundation of spacetime, it raises profound questions about the nature of reality itself. What we perceive as space, distance, separation, and even time may be emergent properties of a deeper quantum network. This idea challenges Einstein's view of a deterministic universe and paves the way for a new understanding of existence. Quantum computing is also challenging our fundamental ideas about time. In Einstein's theory of relativity, time is a flexible dimension intertwined with space and influenced by gravity. But in quantum mechanics, time behaves in a radically different way. Quantum systems can exhibit time symmetry, where processes can unfold forwards or backwards with equal probability. Quantum experiments have demonstrated this phenomenon, effectively reversing the arrow of time in controlled systems. This challenges one of the most basic assumptions in physics, that time always moves in one direction. The arrow of time as we experience it is tied to the second law of thermodynamics, which states that entropy, the measure of disorder, always increases. But quantum experiments show that in isolated systems, entropy can decrease temporarily, defying classical expectations. These findings have profound implications for how we understand time, causality, and the universe itself. If time is not an intrinsic property of reality, but an emergent phenomenon, it raises questions about the origins of the universe and the possibility of manipulating time in practical ways. Lastly, quantum computing is also making waves in biology. Quantum mechanics plays a surprising role in various biological processes, from photosynthesis to human cognition. Quantum computers are helping scientists uncover these connections, paving the way for a new field known as quantum biology. This new frontier, where physics meets biology, is just one of the many ways quantum computing is transforming our understanding of the world around us. As these breakthroughs unfold, quantum computing is set to push the boundaries of knowledge and continue reshaping how we view the universe.